15 microns. Also in the IRAC bands, in a composite from 3 to 5 microns. Then at longer wavelengths, still over the peak of the dust thermal emission at 350 microns. There's distinction between the morphology present at 15, 350, and 8 microns. So not just important to measure what's going on at the long wavelength, so just assuming the mid-infrared is a box, but it's also important to see from wavelength to wavelength what's happening. And when you redshift this kind of object, ALMA will be tremendously good at doing that, in combination with James Webb to provide a version of the optical and an extremely good version of the mid-infrared. And then to step again and say why it's important to do this at high redshifts. We know from the background radiation intensity that there is as much energy produced in the far infrared, shown by the proximate red curve, compared with the optical and UV, and so this process has remained important out to absolutely to redshift 1 and beyond. The biggest contribution being made recently is that Spitzer has been able to provide very high quality images at 24 microns, which allow about 20% of the background radiation to be resolved into individual sources. Those individual sources have a redshift distribution which extends to 0.7 at the peak and out beyond 1, and so it clearly shows strong evolution of population. At longer wavelengths still, and poorer resolution, ground-based images have resolved approximately 30 to 50% of the background, showing that out at higher redshifts again, there's still quite a lot of emission coming from far-infrared luminous objects. And we've got more information than just the backgrounds, but it's more difficult to compare the relative intensity if you look at the distribution of fluxes than if you just look at the background level directly. Now, an example of a region which shows the relative strength of emission at different wavelengths is this now 6-year-old image of the cluster Abell 1835, showing the optical members of the cluster and background galaxies, and then highlighting in contours the far infrared redshifted emission from background objects, magnified by a factor of order of 2 to 3, in this case from redshifts 2.5 and 2.3 for the most powerful sources of emission. And it shows that our current capabilities allow us only to see a very small fraction of the total galaxies present in the far infrared. Now, the energy coming from these galaxies is comparable to the energy from all the optical galaxies in the background of the cluster, but only 2 are very significantly detected. ALMA will revolutionize this and give us a picture in the far infrared, redshifted to the submillimeter, which matches the optical resolution. There's about 25 images of clusters like this. Many of them have got redshifts, and by adding Spitzer information as well, we get a better idea of the spectral energy distribution of these galaxies and find new examples. The problem we have, though, so far is almost every example of a galaxy with a good SED and a multi-wavelength study are all in the ultraluminous class. They don't connect with the well-established luminosity function of galaxies from line of break surveys and from redshift surveys. They're just separated in flux too much. If we want to go inside galaxies to get information about the astrophysics at the moment, we can do that in an unresolved way. We can get a spectrum of CO rotation lines. I'll show what the molecular gas is doing in ultraluminous galaxies, admittedly. This paper by Kartik-Sheth et al. Shows a multiple image in Abell 2218, detected in the continuum in the submillimeter shown by the contours, and then with an image from the OVRO interferometer overlay showing individual detections of line emission associated with CO at each of the centers of the 3 multiple images, and there it is overlaid on the HST image. This provides us with an estimate of the mass of these objects, estimate of the mass of the molecular gas inside, which is typically comparable to the stellar mass you estimate from the optical colors, and is associated with objects of 10 to the 11 solar masses, also within a few kiloparsecs. So they're not only luminous objects, they're also massive objects. So we're looking at the top end of the mass function and the luminosity function happening at moderate redshifts here at 2.5. In some cases you can get higher quality spectra. This shows a small galaxy in another cluster field which is magnified to give a very high quality spectrum from the flat-edged difframeter. And another example of a galaxy not lensed, no, it is lensed this time, yeah, Evolve 851 good source, which is actually, although a single object in the discovery images at sub-millimeter wavelengths, is split into two, each of which has an individual detection at higher resolution from the ERAM interferometer and a very clearly defined velocity width, hopefully giving some idea about the dynamical mass of that system. This is also possible to extend to the infrared. As yet, I don't have any information about the nature of these things in an IFU spectrum, but from a long slit spectrograph, you can certainly see velocity structure inside these galaxies. It shows a NIRSpec two-dimensional spectrum of both H-alpha and nitrogen-2, with some extension and some shear in the line running through the middle of this galaxy in the HDF. We've got about 25 of these spectra, and according to whether the optical lines in these galaxies are identified with AGN emission or not, then you can see a relatively strong or weak underlying broad line component in an infrared spectrum, in principle telling us a bit more information about the power source and whether there's an AGN present and how much it controls the luminosity of these objects. We've been trying to get some metallicity estimates from oxygen line ratios, which is coming along but is time consuming, and hopefully is something which will become much more easy with adaptive optics over the next few years. So we can also, I think still it's viable to target the brightest examples of integral field units, but only the brightest objects at present, and I think we're going to do much better when different facilities come along, but ALMA particularly. The redshift distribution we found so far for the things that have been identified in both and in the field from a combination of radio surveys and submillimeter imaging led by Scott Chapman, who's just moved out of Caltech to Victoria, has established that there's a broad peak in the redshift distribution of these galaxies at about 2.5. So it doesn't push us immediately to reionization, but there is a tail present which we can select. And the results that this has demonstrated, I think, is that we can certainly identify galaxies at the peak of activity. We've got selection effects against detecting lines at desert redshifts and against detecting objects which are not visible in the radio to allow us a fine location at high redshifts. But we've got approximately 50 to 60% of the population of identified sources which have got redshifts now. So we're pretty sure about the population being a distant one and an ultra-luminous one. Based on the number of redshifts, we can also put together a luminosity function. And this is basically the thing which, over the next few years, we hope to establish more firmly and to really understand why the luminosity function of galaxies is evolving so strongly. This is comparing the low redshift luminosity function of ultraluminous galaxies and dusty galaxies shown by IRAS here at 10 to the 12th solar luminous, so it's already at the bright end of this, and exquisite measurements of the optical luminosity function would take us over to the left from here, so we're looking at the most extreme objects. But if we move up to redshift 1 and redshift 2.5, then there's clearly strong evolution taking place. But only at the top end. We can't see galaxies which connect up to where the Lyman break galaxies would lie on this plot. And what we need is a mix of Spitzer information and significant redshift sampling from Spitzer to push us together at redshift 1 in this region, and also at higher redshifts being able to make more sensitive observations to push down from many 10 to the 12th solar luminosity objects that can currently be detected down to the same down to the top end of the luminosity function defined by the Lyman break galaxies to get a picture of the whole range of galaxy luminosities which are present. And we've seen this already so far to see the rate of evolution of star formation with redshift, and the goods results tend to indicate that there's a high level of optically visible star formation continuing out to redshift beyond 6. The results from the dust-enshrouded objects and their redshift distribution indicates that about that redshift that the dust gives way again to optically visible radiation dominating the luminosity of galaxies. But at the intermediate redshifts from 1 to 4, optics take most of the power. And so when we go back to reionization, we're probably likely to see a a minority of energy coming out of galaxies that ALMA can detect, but we'll be able to detect them still with extremely high sensitivity. So let me show quickly what we can do with, wrong button. This is what can currently be achieved with facilities that can image CO at low redshift. You can provide images which match in quality, dynamic range and sensitivity, what can be done with CO in red, what can be done with H alpha in green, and what can be seen in the radio continuum and the optical continuum in blue. You can get very fine quality maps of CO here in two different transitions over a galaxy, over two galaxies, showing how the different HST properties correlate with the places where the molecular gas is present, and then also see in the molecular gas that's detected by the interferometer, you can see velocity gradients and really get a way of seeing the dynamics of both intense star formation regions and the whole galaxy. Now, this takes, at the moment, many hours of integration, but the impression to leave from ALMA is this can be done at high redshifts with this comparable resolution covering an arc second or two across in a matter of hours. And so ALMA can do a few of these galaxies a day, directly probing star formation at high redshift. And ultimately, I guess this can also be done with radio telescopes, but ALMA is going to be along first. And ALMA can exploit the lensing effects very efficiently too. Depending on whether or not the density profile has a core or not, you may be able to see background galaxies congregating in the center.